So my network jammed, so sorry for that interruption. So we continue from where we ended. So we saw all these factors affecting AB, blood pressure. Now we'll continue to look at how arterial blood pressure is regulated. So the regulation of blood pressure is very important because regulation actually will lead to the maintenance of your blood pressure and to ensure that all things are working well. So blood pressure can be regulated neurally. That is mean through the nerves. And this is found in the medulla oblongata. And this can be done via the vasomotor centers and then the cardioinhibitory center. The vasomotor centers will lead to activation of the sympathetic aspect of the autonomic nervous system. And the cardioinhibitory centers will lead to the activation of the parasympathetic fibers, that is the vagal nerve of the autonomic nervous system. So cardiac control centers, we can have cardiac accelerator center, which will lead to increased heartbeat, and regulatory inhibitory center lead to what? Decreased heartbeat. So the regulatory mechanisms will depend on fast-acting reflex activities, which are leading to the control of the cardiac output, which involve the stroke volume and the heart rate and the peripheral resistance. And the long-term mechanism will be done by the blood volume. So we'll be looking at all this one by one. So let's look at regulation of arterial blood pressure. The regulation of cardiac output is a fast-acting mechanism. We know this already. And this will be done by the Frank-Starling mechanism, where it is geared towards the stroke volume, where sympathetic nerves will act on the end diastolic volume and the contraction length. And then this is going to kind of regulate the mean arterial blood pressure. Now, sympathetic nervous system can also regulate the heart rate by working directly on the sinoatrial node, by the binding of the noradrenaline to the beta-1 receptors, leading to faster heartbeat. And then we can also have parasympathetic also working on the heart rate. So sympathetic can work on both variables of the cardiac output, but the parasympathetic works on only the heart rate. Now let's look at how we can regulate peripheral resistance. So regulation of peripheral resistance can be intrinsic, extrinsic, and paracrine. The extrinsic mechanism is controlled through several. We'll be basing our talk on mainly on extrinsic. You can read on the intrinsic and the paracrine control. So intrinsic mechanism is controlled through several reflex mechanisms. And the most important ones we're going to look at are the baroreceptor reflex and the chemoreceptor reflex mechanism. Now, baroreceptor, when we say baro, you know that we are looking at barometer is pressure. So baroreceptors are receptors that are found within the carotid sinus and the aortic arch, which are able to detect differences in the pressure changes when blood is pumped from the heart through the aorta or the carotid sinus. So, for instance, when there is a change in the blood pressure, such that the blood pressure increases, there is a positive baroreceptor activity. This positive baroreceptor activity is going to lead to the activation of the equivolar activation of the vasomotor center, leading to a sympathetic activity. And this sympathetic activity will lead to some form of vasodilation. And when there is vasodilation, there is a decrease in total peripheral resistance. And this same baroreceptor mechanism can also activate the parasympathetic mechanism, leading to the slowing of the activation of the sinoatrial node, leading to a decrease in the cardiac output. For chemoreceptor mechanism, we are looking at some chemokines, especially, for instance, chemical changes in the blood when we have low oxygen or high carbon dioxide, or the pH changes. So, for instance, when there are hemorrhagic conditions, there's going to be low blood pressure leading to hypoxia. This is going to activate the chemoreceptors, which is going to have equivalent activity on the cardioinhibitory center, but a positive activity on the vasomotor center. And when there is a positive activity on the vasomotor center, this is going to lead to the adrenal medulla activation to release some form of adrenaline, which binds to the alpha receptors of the blood vessels, leading to a vasoconstriction. And when there is vasoconstriction, this will lead to increased total peripheral resistance, leading to a higher pressure. Also, there is going to be some form of activation of the heart rate, leading to its increase via the parasympathetic mechanism. There are other vasomotor reflexes. So first, we saw the baroreceptor mechanisms. We saw the chemoreceptor. Now we're also looking, and these are all fast-acting mechanisms. We are looking at some other vasomotor reflexes. We can also look at the atrial stretch, the length at which the atrium will stretch. And when there is, for instance, when there is increased venous return, we expect that the atrium will stretch more, leading to a positive atrial stretch receptor, and eventually this is going to lead to reflex vasodilation and then decreased pressure. Amount of heat present will also determine what happens. Exposure to heat will lead to vasodilation so that the body can cool, and then exposure to cold will lead to vasoconstriction so that some form of heat can be maintained in the body. So when there is vasodilation, indirectly we are going to have low blood pressure, and when there is vasoconstriction, you are going to have some form of high blood pressure. Then we can also have the pulmonary receptor mechanism, where there is lung inflation leading to vasoconstriction. The last one here is the hormonal agents. We have seen these things already. Noradrenaline leading to vasoconstriction, adrenaline vasoconstriction, angiotensin leading to vasoconstriction, vasopressin leading to vasoconstriction. Now that we've spoken about regulating cardiac output, let us see how we can regulate the blood volume. The blood volume. So the blood volume is usually mainly by renal activities, and it is a long-term regulatory mechanism. And since it is mainly renal, the pathways that are involved in this are the renin-angiotensin system, the antidiuretic hormones, or the vasopressin mechanism, and then the low pressure volume receptor mechanism. For the renin-angiotensin system, what happens is that we are looking at the retention of sodium. The amount of sodium that will be retained will also regulate the amount of blood volume that is maintained. So what we are trying to say here is that when we take for instance, when we're dealing with osmolarity or osmosis, we realize that the movement of water will depend on the amount of electrolytes that are maintained at one aspect of the membrane. So it states that electrolytes will always draw water nearer to themselves. So what happens is that when there is a drop in the renal flow, there is going to be low amount of sodium. And when there is low amount of sodium, this information is going to be given to the brain. And then this is going to send a signal back to the juxtamedullary apparatus of the kidney, leading to the release of renin. This renin will convert angiotensin to angiotensin 1. And then the angiotensin 1 will convert, which is a converting enzyme. So the angiotensin 1 will be converted to angiotensin 2 by angiotensin converting enzyme. And then the angiotensin 2 can also be converted to angiotensin 3 by the same angiotensin converted enzyme. And these things will lead to vasoconstriction. And then when there's vasoconstriction, tells us that they are going to lead to some form of what? Retention. Now, angiotensin 2 will lead to the conversion of corticosterone to aldosterone in the adrenal cortex of the adrenal gland. And then aldosterone is what is going to lead to the retention of sodium. And when sodium is there's retention of sodium, then that means that we can have what? Water also being retained. The antidiuretic hormone or the vasopressin will work based on the water component of the body. So when there is hypovolemia or dehydration, this is going to activate the osmoreceptors in the hypothalamus, which will lead to the release of ADH from the posterior pituitary gland. And when there is the release of ADH from the posterior pituitary gland, ADH will cause water reabsorption at the kidney tubules. That is the proximal and the distal convoluted tubule. Now, low pressure volume receptors, we call something the ANP hormone, which is secreted from the walls of the right atrium to regulate sodium excretion in order to maintain blood. So in effect, we are saying that for you to regulate blood pressure, which is equal to cardiac output times peripheral resistance, you can do that by regulating the cardiac output, which can be done neurally or chemically, or you can also regulate the amount of blood volume. And then these things can also be done via low pressure volume receptors, antidiuretic hormone, and then renin-angiotensin mechanism. So we say regulation of the volume will be dependent mainly by renal activity. So if you have kidney problems, that is when you can also have higher blood pressure. Thank you very much for this section of lecture. If there are no questions, we will meet next week. Have a wonderful day.